In this video, we're going to explore the synthesis of ethers and those cyclic triangular ethers known as epoxides. We're going to look at some old stuff and some new stuff. Williamson ether synthesis, we did an SN2 reaction with an alkoxide nucleophile, that is R attached to O-, an appropriate carbon with a leaving group, we call that Rx. Here's methoxide. Here is 3-bromoheptane. Looks like an S stereocenter. Here's a polar aprotic solvent, dimethylformamide. If you did an analysis in Chapter 9, you have a secondary carbon. We don't know SN1 or SN2. We have a strong nucleophile. We're leaning towards SN2. And a polar aprotic solvent. We have concluded SN2. Here are the results of an SN2. There will be a stereochemical inversion, creating a methoxy ether right here. And its name is right here. Two names, R3-methoxyheptane and R3-heptylmethyl ether. Please consult the video on naming ethers. We can also add an alcohol to an alkene in the exact same fashion that we added water to an alkene. The mechanisms are indistinguishable except your nucleophile is not water. It's an alcohol, and the catalyst is exactly the same as in 6.1b. Sulfuric acid on the right, or toluene sulfonic acid on the left. And the results are the major product being Markovnikov with the O on the more substituted carbon, and the H went here. And the name for that would be isopropyl cyclohexyl ether with an ethyl on the cyclohexyl as well. So we call it 1-ethyl cyclohexyl as one of the groups on the ether. Pink isopropyl, the other group on the ether. Sorry, I didn't have any color coding here. I'll fix that shortly. Or you can name it with an isopropoxy group, this group here, attached to cyclohexane. That's the major Markovnikov product. You'd get a small amount of the minor anti-Markovnikov product. The only thing changing in the names are the numbers. And the anti-Markovnikov alcohol has these two names now color-coded. Moving on. We can form a vicinal halidehydrin as we did in section 6.1f by reacting an alkene with a halogen in water. Iodine, bromine, or chlorine, and you get a vicinal halidehydrin, and it's an enantiomer with the Markovnikov O on the more substituted carbon because it's more electronegative, and the less electronegative I on the less substituted carbon. And they are anti to each other because there was a triangular iodonium intermediate formed in the mechanism, and water did a backside attack on that. Now, if I can take this proton off this oxygen, I will create a nucleophile in the same molecule as I have a leaving group. That brings to mind the neighboring group participation found in section 9.4. Hydroxide base would do the job. You'd get an intermediate O-. As soon as it sees a carbon with a leaving group, it's going to do a backside attack. We'll even throw a mechanism on there. Lone pair attacks the carbon with a leaving group. Leaving group does what leaving groups do. It leaves, and we're going to create this result. We've got this ether here, cyclic ether known as an epoxide. That's what we're forming here, is epoxide. Just modified my title here. I did the epoxide, the O did a backside attack, and the iodine left. There it is, the O. And I just redrew it with a little rotation. And look at the names. You can name it after the original alkene, trans-3-methyl-3-hexene, and throw epoxide at the end. Not quite as descriptive as this name here, which has the stereocenters, and it names specifically this one enantiomer and not the other that would be formed from the enantiomer of this molecule over here. We can name this pink piece as oxyrane with groups on 2 and 3. It's a heterocycle, and that would be its name there. And we're going to look at a couple new reactions. We're going to react an alkene with a per acid. Per in this context has the same connotation as per iodate or per iodic acid. One more oxygen than iodic acid. And there we have a percarboxylic acid. It has a third O. I'd like to point out this is the O that's important. It will be the one that makes the ether. Ether here will look similar to these two, but I picked the other enantiomer this time. Oh, wait a minute. No, I did not. I started with a different alkene. So I would get this molecule with its enantiomer. The name is a little different. I may have to verify this second stereocenter. I had to fix that. I had the wrong stereocenter there. It's a diastereomer of this molecule up here. Here's the other name. 2R3S 2,3-dimethyl diethyl 2-methyloxyrane. Keeping in mind that an E-alkene always gives a trans epoxide, and a Z-alkene always gives a cis epoxide. Or using this nomenclature, it's easy to remember. Trans begets trans, and cis begets cis. Notice the two ethyl groups are on the same side here, and they started on the same side here as well. Here the ethyl's up and down and up and down. And it's all because backside attack and the syn addition of the iodine to make the triangle. A lot of talk. Moving on. Condensation of two alcohols is a new reaction. Condensation is not entirely new. Bringing two molecules together to make a larger molecule while losing, you guessed it, water in the middle. We're going to take one propanol and isopropanol, similar catalyst we've been using all semester. Sulfuric acid or toluene sulfonic acid. The little product is, yes, water. And the big product should be an ether. And we have a propyl group on one side and an isopropyl on the other. You can use the common name, isopropyl ether, listed alphabetically. Or we can say the longest chain of continuous carbons in the molecule is 3 for a propane. And there's an isopropoxy attached to the first carbon of that chain. And that's the second name, 1-isopropoxy propane. So we now have a method of making many methods, and epoxides. I hope you found this video useful, and I look forward to our next video.